Hello dear students. This session is the revision class of nuclear magnetic resonance spectroscopy, which is also called as NMR spectroscopy. So from the exam point of view and also from the future point of view, if you are interested in doing research or studying masters in organic chemistry, so the study of nuclear magnetic resonance spectroscopy is very important. We have to understand the concepts of NMR spectroscopy and why it is used, what are its applications, and how to handle the NMR spectroscopic instrument. So all this is very important. So now I am going to revise the class NMR spectroscopy. So what we are going to understand in NMR spectroscopy? What is NMR spectroscopy actually? So this involves the absorption of electromagnetic radiation in the radio frequency region, that is between 3 into 10 raised to 6 hertz to the 3 into 10 raised to 10 hertz. Okay, so in between this electromagnetic wavelength, so the organic compounds, they are going to absorb the electromagnetic radiations, so that is recorded with the help of NMR instrument. So absorption of radio frequency in the presence of magnetic field results in nuclear magnetic resonance spectrum. So this spectroscopic method is used in the identification of organic compounds mainly because so the widely used NMR techniques are, one is proton NMR and another one is C13 NMR. So these two are the very important NMR techniques. So what we are going to use, so the proton NMR will give the count of protons, how many protons are present, and the C13 NMR will give how many carbon is present in that particular organic compound, and also in which or what sort of environment so those proton and carbon are located, and what are the neighboring atoms or groups which are present. So all this structural analysis can be done with the help of nuclear magnetic resonance spectroscopy. So now we'll see the theory of NMR spectroscopy. So the nuclei of atoms with odd numbers and of protons or odd number of neutrons or odd number of protons and neutrons possess resultant nuclear spin. So not all the atoms or the nuclei which are present, so they will possess the nuclear magnetic resonance. No, very simple, means very few, like those nuclei of the atoms which have odd number of protons or odd number of neutrons, or both odd number of protons and neutrons, they only will possess the nuclear spin. So such a spinning nucleus produces a magnetic field and hence behaves as a tiny magnet. Okay, so let us imagine this as a spinning nucleus and it acts as a tiny magnet. So as we all know, so the magnets will attract each other. The two magnets are going to attract each other. Okay, so this is the degenerate form of the nucleus. So how we can understand this is, so just like how in the absence of a class teacher, so the students will be in the degenerated form. That means so they are randomly oriented. That some of the students will be coming inside the class and some will be going outside the class, some will be talking to their friends who are sitting backside in the last benches. So like this, the students will be randomly oriented in the absence of class teacher. Whereas as soon as the class teacher enters inside, so all the students, they will sit in their own places, they will not turn back or they will not go outside. That means here we can understand that so a class teacher is a external magnetic field which is going to be applied, and the students can be compared to the nuclei. Okay, so in the same way here, when there is no external magnetic field, so the nuclear magnets are randomly oriented. Whereas when in magnetic field is applied, that is B naught, a magnetic field, external magnetic field is applied, so the nuclear magnets are oriented with or against B naught. Okay, so they can get oriented in two different ways. That is, one is so they can get oriented in a parallel orientation. Parallel orientation is because, or it is due to the lower energy. That means the nuclei, it will get oriented or it will start moving towards the external magnetic field. It will not feel any opposition because the way it is moving is towards the flow of external magnetic field. In the same way, another type of orientation which is possible is so anti-parallel orientation. To get aligned in this anti-parallel orientation, that nuclei, that particular nuclei should possess higher energy. That means it is getting aligned in the opposite direction of the external magnetic field. Okay, so these are the two types of orientations which a nuclei can take. Now we will see the principle or the theory further what it is going to explain about. So in the presence of a magnetic field, as I told, the spinning protons are going to precess. Okay, so the precession frequency increases with the increase in strength of the applied magnetic field. As the precision frequency increases, the energy difference, that is delta E, we call it as delta E, the energy difference between the two orientations increases. Then we will have a change in energy which is given by h nu, where nu is the precision frequency. Okay, so this is what is going to happen in the applied magnetic field. The nuclei behaves like this. A radio frequency. Okay, so a radio frequency radiation is applied to such a proton and it is gradually increased. When the frequency of applied radiation becomes equal to the frequency of the precision, a state of resonance is reached. At this moment, the protons in the lower energy state absorb energy and changes their orientation to higher energy state. Okay, so the nuclei, it is going to absorb the higher energy state and it will change its orientation. It will get flipped. So that is why this is called as flipping of protons. The absorption of energy is detected by a radio frequency detector which gives a signal to the recorder. So this is the basic principle of NMR. So when a proton is used for resonance, so it is called as NMR and it is represented as PMR, what is called as proton magnetic resonance. Okay, so now what is the relationship between applied magnetic field and resonating frequency? So this is the equation which defines the relationship between the applied magnetic field and resonating frequency. Here nu is called as resonating frequency and B naught is the applied magnetic field and gamma is the gyromagnetic ratio and it depends upon the resonating nucleus. Okay, so we all know that for a proton, that is gamma is equals to 2.67 into 10 raised to 8 anta. Okay, so this is the gyromagnetic ratio. By knowing this, so we can find out what is the frequency or the precision frequency of that particular nuclei. So this is the principle of NMR spectroscopy. And next is, so we have to be very familiar with the shielding and deshielding effect. What is meant by shielding and deshielding effect? By knowing this only, if we have given a spectrum of any of the organic compound and if anyone asks us to interpret it, so we need to know the shielding and deshielding effect. Then only we can assign the values of NMR properly and we can characterize the compound and we can name the compound or identify the compound. To this, knowing about shielding and deshielding is very important. Now what is meant by shielding? As I told, the precision frequency of a bare proton can be calculated theoretically using the equation nu is equals to gamma B naught divided by 2 pi. This is for a bare proton. Bare proton means what? So it doesn't have any of the electrons which are revolving around it. It is one single proton, bare proton, which is present. If all the protons in a compound are bare protons, they should resonate at the same frequency and a single signal should be obtained for all protons. Just like how we see for a TMS, tetramethylsilane. So so all the 12 protons which are are present, they are chemically equivalent, and we are going to get one distinct peak is observed. So that is in case of bare protons, but practically in compounds the protons are present in different chemical environments. Okay, say for example if we take bromoethane, so there the protons CH3 CH2, though they are in different chemical environments, so the electrons present around the protons influence the magnetic field experienced by protons. As a result of this, so the protons resonate at a different frequency than the theoretical values. So this is the reason why we observe shielding and deshielding effect in case of organic compounds while studying the NMR concept. So if the electron density around the proton is high, the circulating electrons produce a magnetic field which opposes the applied field. So thus what happens, the effective magnetic field experienced by the proton decreases. So this will result in the lower precision frequency, and the proton come to the resonance at a lower frequency. In the presence of shielding effect, a higher magnetic field is required to make the proton to resonate at the theoretical value. Okay, so thus the effective magnetic field which is experienced by the proton decreases in case of having the high electron density around the proton, and this will result in the lower precision frequency, and the protons come to the resonance at a lower frequency. So this is what is called as shielding effect, or it is also called as diamagnetic effect. And since the shielding effect requires higher magnetic field to make a proton to resonate, so this is called as upfield. This is also called as shielding effect, is also called as upfield. And whereas in case of deshielding effect, this is caused or this is observed when the electron density around the proton is less. Okay, it experiences a higher amount of magnetic field than expected. Therefore, so its precision frequency increases and it resonates at higher frequency. Okay, so the higher frequency is required for the nuclei to have a resonance. So this is called as deshielding effect or paramagnetic effect. In the presence of deshielding effect, the protons resonates at higher frequency than expected. So that is why here a lower magnetic field is sufficient to make the proton to resonate at the expected frequency, and hence it resonates downfield. Okay, so this is how we can represent it. So here this arrow mark shows that the increase in frequency. So in case of shielded nuclei, since the proton experiences a smaller effective magnetic field here, so the resonance at lower frequency is observed, and that is why it is called as more shielded or upfielded. Whereas for the deshielded nuclei, so the protons experience a higher effective magnetic field and hence come into the resonance at higher frequency. So this is the higher frequency region. So that is why it is less shielded, or it is also called as down shielded. So this figure represents the shielding and deshielding effect. And next important thing what we have to see in this chapter is instrumentation of NMR spectroscopy. So this is very important. So this is the schematic diagram which explains the NMR spectroscopy. So 5 different parts are observed here. So this instrument consists of 5 parts. In that, so the first one is a sample holder. So as I have discussed in the class, so it should be inert. Sample holder should be inert and should allow the radio frequency radiation to pass through it. Okay, so the organic compound along with the reference compound dissolved in a suitable solvent is taken in this sample holder. So this is what is called a sample holder. And next is magnets. So since this is as the name itself says, nuclear magnetic resonance, that means external magnetic field, a high efficient external magnetic field is required. So that is why we are going to use magnets anta. So those magnets are superconducting magnets. So the sample is kept between these two magnets. So the magnets produce strong magnetic field of known value. So the magnetic field should be uniform and act in the same direction. So this is what we have to keep in our mind. And next, a radio frequency generator is required. The sample is exposed to the radio frequency radiation from a radio frequency generator. Okay, so this is what a radio frequency generator. And next is radio frequency detector and amplifier. Okay, so radio frequency detector is connected here, and to that amplifier is connected. And next, the last part is a recorder. So a bar chart recorder or a computer records the signal from the radio frequency detector. Okay, so this is what an instrumentation of NMR spectroscopy describes about. And next is, what are the solvents used in PMR? For PMR, the solvent preferably should not contain any protons, because that protons which are present in the solvent only will give numerous of peaks in the spectrum, and it will become very difficult for us to interpret it, and which proton is of due to the reason of which, whether it is because of our organic compound which is under examination, or do those protons are because of the solvents. So this confusion will be there. So for that reason, so the solvents which we are going to use in NMR spectroscopy, preferably they should not contain any protons. The solution should be free from paramagnetic and insoluble impurities, and usually deuterated solvents are used. Deuterated means the hydrogen will be, that is the proton will be removed and it will get deuterated. So chloroform D1 is the most commonly employed for PMR, and other commonly used solvents for organic compounds, that especially organic compounds, are CCl4, CD3CN, that is acetonitrile. So acetonitrile, here hydrogen, 3 hydrogens are deuterated into deuterated form, that is CD3CN, and DMSO D6, C6D6. So these are some of the organic compounds which are especially used as solvents in PMR. And next is chemical shift. So the position at which a signal occurs in NMR spectrum is called as a chemical shift. So in NMR spectroscopy, a reference compound is mixed with a sample compound. The position of the signal from the sample is determined relative to the signal from the reference compound. So here tetramethylsilane or TMS is used as a most common reference compound, and TMS produces a very distinct signal at a very low frequency. So how do we define a chemical shift? It is the distance of the radio frequency signal of the protons of the sample compound from the TMS signal. Okay, in delta scale it is expressed in ppm. So this is how we are going to calculate the chemical shift. So chemical shift delta is equals to new sample minus new reference divided by new reference into 10 raised to 6. So here new is the frequency. So this is frequency of signal from the sample. New sample means frequency of signal from the sample, and frequency of the signal from TMS, reference is TMS, we are going to use TMS as reference, and new reference or nu naught, we can call it as nu naught, this is the operating frequency. And okay, so you can change this in your textbook, it is nu naught only. So nu naught is the operating frequency, and this is new TMS, that is frequency signal from the TMS. Okay, so this is how we are going to calculate the chemical shift. And next is what are the advantages of using tetramethylsilane as reference? So as I told, so the tetramethylsilane, it has got 12 protons which are chemically equivalent. That means all the protons have got the same chemical environment. So that is why, so it will give a single intense peak. Okay, and next is the protons in TMS are highly shielded. Highly shielded means they have got a dense electron cloud, therefore they produce a distinct peak. Distinct means there we will not find out any splitting pattern. Splitting is not observed there. We will get only one distinct peak, that too at very low frequency. And next is TMS is highly volatile, hence it can be easily separated. Highly volatile means it will get evaporated easily. TMS will get evaporated if we take it in a beaker and keep it outside on the table itself. So by 2 to 3 minutes all the chemical will get evaporated. So that means it is highly volatile and hence it can be easily separated from the sample compound just by evaporation. And TMS is soluble in most of the solvents which is used in NMR spectroscopy, and it is chemically inert. Okay, so that is why these are the advantages to use tetramethylsilane as a reference. And next is so how to calculate or how to distinguish the number of signals in NMR spectrum. So the protons present in the same environment are called chemically equivalent protons. A set of chemically equivalent protons produce a single signal in the NMR spectrum. So now let us take an example of ethanol. So here CH3, CH2, OH. So here if we can observe, so here three different protons are present which are present in three different chemical environment. So the three methyl protons, that is CH3, here three methyl protons are present. So they are marked as A. And the two methylene protons, that is CH2, two protons which are present in this methylene group are marked as B. And in the same way, so here OH in this hydroxy group, so the proton which is present here, this is marked as C. And therefore, so we have the three different set of protons present in this ethanol which have a different chemical environment. So that is the reason we are going to get three signals in this NMR spectrum. For ethanol we are going to get three signals. Okay, so next if we take the example of this, so here this is a methyl group and this is a methyl group. So these two have a same chemical environment, that is why they are named as A. But the proton which is present here, this has a different chemical environment, so that is why it is marked as B. And for this compound we are going to get two signals. In the same way, so here for this compound all the 6 protons are in same environment, so that is why we are going to get single signal length. And next is so to this compound, so here all the 6 protons are chemically equivalent and therefore one signal is produced. Okay, so in this way we are going to calculate the number of signals in NMR spectrum. And next important thing what we have to see in NMR spectroscopy is splitting of signals, or it is also called as spin-spin coupling. The interaction of the protons producing the signal with the protons in the neighboring group may cause the splitting of the signal in NMR spectrum. This is called as spin-spin coupling. The number of peaks in the signal is called signal multiplicity. The set of protons responsible for the signal will not cause any splitting. The protons present in neighboring group are responsible for splitting. The multiplicity of the signal, that is the number of peaks in the signal, can be obtained using n+1 rule. According to this n+1 rule, if there are n chemically equivalent protons in the neighboring group, so the signal will be split into n+1 peaks. That means if there are n number of protons, say for example if there are 2 protons are present, then the signal what we are going to get is 2 plus 1, that is which is equal to 3. Okay, so if there are 3 protons are present, then we are going to get the signal as 3 plus 1, that is 4 signals are obtained. Okay, so if we take the example of bromoethane here, so for bromoethane has got two different set of protons which are present in two different chemical environments. So here for this CH2 group which I have called as B, so CH2 proton causes the splitting of signal from CH3. So CH3 is the neighboring group which is present to the CH2 here. CH3 is the neighboring group. So that is why the splitting pattern of this CH2 methylene group depends upon methyl group, that is CH3. That means for CH2 here, since 3 hydrogen or 3 protons are present, 3 plus 1 is equals to 4. That is why for methylene we have to get so 4 peaks. Okay, so we will get 4 peaks. In the same way, for this methyl group CH3, the neighboring group is CH2. Since there are 2 protons are present, 2 plus 1 is equals to 3. So therefore, for CH2 group, so we are going to get 3 peaks, which is called as a triplet anta. Okay, so for CH3 protons, so the signal will split into 3 plus 1, which is equals to 4, and it is called as a quartet anta. Okay, and next is a coupling constant. What is meant by a coupling constant? Coupling constant is the distance between the two adjacent peaks of a split in a NMR signal. Okay, so that is, say for example, if we have got a doublet or a triplet, so here in this triplet, what is the distance between this intense peak and the neighboring peaks? So this distance is calculated as a coupling constant. If a set of protons B, so this is B, if a set of proton B splits the signal from a set of proton A, then the coupling constant is denoted as JAB. Okay, so this is what is represented as JAB. And in the same way, if a set of protons A splits the signals from a set of protons B, then the coupling constant is denoted as JBA. So here, if you can see the pointer, what I am pointing out and showing, so this is the distance which is denoted as JBA. Okay, so it is found that JAB minus JBA, hence the protons on the adjacent carbon atoms can be identified from the same coupling constants of their signals, and the unit of coupling constant is Hertz. Okay, so we are going to use Hertz to measure the coupling constants. So this is what about coupling constant. And next important thing is factors affecting the chemical shift. So the positions of signal in NMR spectrum is decided by shielding and deshielding of the protons. Deshielding of the protons shift the signals towards the higher frequency, that is, so higher delta value or downfield, whereas shielding effect shifts the signals towards the lower frequency or upfield. So some of the factors which affect shielding and deshielding and hence the position of the signals in the spectra are, so the first one is the presence of electron withdrawing groups or atoms of high electronegativity. As the electronegativity or electron withdrawing character of the group attached increases, the deshielding effect increases. Okay, hence when the deshielding effect is increasing, the signal shifts towards the higher frequency or higher delta value. The deshielding effect decreases as the distance of the proton from electron withdrawing or electronegative groups. Okay, next is van der Waals deshielding. Another factor which affects the chemical shift is van der Waals deshielding. When a proton occupies a sterically hindered position, that means if there are so many neutrons or electrons which are present around the proton, it automatically possesses the spherical hindrance. The electron clouds of surrounding groups produce a deshielding effect. The signal from such a proton shifts towards higher frequency region, and this is what is called as a van der Waals deshielding. But this effect occurs in a negligible extent. We will not observe more of a van der Waals effect. In very negligible cases, van der Waals effect is observed. And another important factor which affects the chemical shift is the anisotropic effect. So this is found in organic compounds, that too especially which contain carbon-carbon pi bonds. The pi electrons are less tightly held by the nuclei compared to the sigma bonded electrons. Hence, they move freely in response to the applied magnetic field. When the applied magnetic field is increased, so the electrons move in a circular path. So they will create a circular path. So the effect of this induced magnetic field depends upon the direction of the region of the proton. If the induced magnetic field is in the direction, means along the direction of the applied magnetic field, then the resonance occurs at higher frequency and delta value increases. If the protons in the aromatic ring or aldehyde group say for example a carboxylic group or a alkane carbon, so then it increases the delta value, and this effect is called as anisotropic effect. And if the induced field is against the applied magnetic field near the proton, then the proton resonates at at a lower frequency, and the signal appears at a lower delta value, and this phenomenon is observed in alkyne protons. And next is approximate chemical shift values for different types of protons. So let me start from the lower frequency. So from the lower frequency towards the higher frequency region, if we can observe it, so in between 0 to 1.5 ppm, so we are going to get saturated compounds, and in between 2 to 3.5 ppm, that is ppm is the delta value what I am expressing, so alkyne protons are observed, and in between 3 to 5 ppm, so we are going to get alcohol protons, and in between 5 to 6.5 alkene protons are observed, and in between 6.5 or 6 to 8 aromatic protons like benzene derived organic compounds are going to get observed, and in between 9 to 10 ppm, so we are going to get aldehyde protons, and in between 10 to 12 ppm we are going to get carboxylic acid protons anta. Okay, so what does it mean? Say for example, if an organic compound has got a aromatic ring, so then the protons which are present in that aromatic ring, so that is going to get appear, the peak of that particular protons will be observed in between 6 to 8 ppm. That means we measure it in terms of chemical shift, so we are going to get the signal in this particular region, and in the same way, so between 9 to 11 we are going to get aldehyde protons anta. Okay, so this is the approximate chemical shift values for different types of protons. And next, moving on to the advantages of NMR spectroscopy. So this is very important. Only when you know what are the applications or advantages of this particular spectroscopic technique, so then only we can implement it in various different studies which we are going to take in future, that especially if we do any research, this NMR spectroscopy is very important. So that is why it is very essential to know about the advantages. The very first advantage is a small amount of organic compound is sufficient. We need not to synthesize it in grams or kgs, very small, that too in mg, milligram of a compound is more than enough to get a spectrum. And the next advantage is the organic compound can be recovered after obtaining the spectrum, and the third one is the sample can be easily prepared by mixing the organic compound with the suitable solvent and a reference compound. And next advantage is spectrum is simple, therefore the analysis of compound is easy compared to other spectroscopic methods. And okay, so next is analysis of NMR spectroscopy. So how to analyze a NMR spectra? If anyone gives a spectrum and asks us to interpret it, what and all the protons are present in this spectra, or how you are going to do the nomenclature of this unknown organic compound, if anyone gives a spectra and asks us to do what and all the informations we have to look forward, how to analyze the NMR spectra is mainly we have to keep 4 points. That is, the first one is the number of signals in the spectrum gives the number of different sets of chemically equivalent protons present in the compound. Okay, so number of protons will define how many different chemically equivalent protons are present. And next is we have to see the position of the signal, that is, so the chemical shift indicates the functional group and the type of protons present and the environment around the proton. This is the second observation what we have to do as soon as we look into the NMR spectra. And the third one is the area under the NMR signal gives the relative number of protons responsible for producing the signal. That means if we have a broad spectrum or broad peak, so that means that particular set of protons are in more in numbers. That is why we call it as relative number of proteins. If the area is more, then obviously it proportionals to the relative number of protons. Okay, so this is what we have to observe. And the fourth one is the signal multiplicity indicates the number of chemically equivalent protons bonded to the adjacent carbon atoms. So these are the four main features what we have to look forward while analyzing NMR spectrum. So now I have taken three examples of organic compounds so that you will clearly understand how to interpret or how to analyze a NMR spectrum. Okay, so the first one is a bromoethane. What I have taken is bromoethane. As we all know, so this is CH3 CH2 Br. This is what is called as bromoethane. So here there are two sets of protons. One is methyl protons and another one is methylene protons. So they are in two different chemically equivalent protons. So therefore, so two signals are obtained. So this is the signal of TMS. You need not to worry about this signal. This is due to TMS. So this signal that is what we are seeing in a triplet form. This is because this signal represents methyl protons, that is CH3, and this is a quartet. Okay, so here quartet why we have got is, so this is the signal which is obtained because of this methylene group. Okay, so now you should understand according to the n+1 rule. So for this methylene group we have got quartet. That is because we have CH3 as a neighboring group. Here 3 protons are present. 3 plus 1 is equals to 4. So that is why we are getting quartet. In the same way, so for this methyl we are getting triplet. That is because CH2 is the neighboring group and here 2 protons are present. 2 plus 1 is equals to 3. So that is why triplet signal is observed. Okay, so the CH2 proton split the signal from CH3 and CH3 proton split the signal from CH2 into quartet. The intensity of triplet is in the ratio 1:2:1. The intensity of the quartet is in the ratio 1:3:3:1. Since the protons of CH2 and CH3 group are in the ratio 2:3, the area under the signal is also in the same ratio. So this is how we are going to analyze bromoethane. And next one is ethanol. So this is the proton NMR spectrum of ethanol. I have taken pure ethanol only. In your textbook there is comparison. One explains about impure ethanol and another one is pure ethanol. Here I am representing it in the pure ethanol form only. So here there are 3 sets of protons. So one is methyl and another one is methylene and another one is hydroxyl. So 3 different chemically equivalent protons are present, so which we can name it as A, B and C. So for this reason we are going to get 3 signals and the area under signals are in the ratio 3:2:1 because of the protons of A, B, C are in the same ratio, and the hydroxyl group, that is OH group or the OH proton, appears at the highest delta value because it experiences highest deshielding effect by oxygen. Since oxygen is present, oxygen is very electronegative, highly electronegative. So here the electronegativity plays the role. Just like how we discussed in the factors affecting the chemical shift, since electronegative atom is present, oxygen, so here OH group will appear at the highest delta value. Okay, and the methylene proton appears at the lower value and CH3 proton appears at the lowest delta value because it experiences least deshielding by the oxygen. The signal from CH3 proton split into triplet by CH2 protons and the signal from the CH2 protons is split into quartet by CH3 protons. Okay, so this is how we are going to do the interpretation of ethanol. And the next one is ethyl acetate. So CH3, COO, CH2, CH3. So ethyl acetate has got 3 different chemical environment having protons. That is, one is CH3 which is shown in green color and another one is CH2 which is shown in red color and another one is CH3. So even though there are two methyl groups CH3 which are located at both ends of ethyl acetate. So the chemical environment of this methyl group is different from the chemical environment of this methyl group. Okay, so why does it so like this? That is because so here the CH3 proton marked A appear at lower frequency, and the signal from CH3 protons marked C, so here this can be marked as C and this can be marked as A, appears at the lowest frequency. And okay, so the signal from CH3C split into triplet by CH2B protons. The signal from the CH2B split into quadruplet, that is CH3C protons. So the signal from CH3A appears as a singlet. It is not involved in the spin-spin coupling because the adjacent carbon does not contain any proton. Okay, so this is the adjacent carbon. So this adjacent carbon, this does not contain any proton. So it has got, see here one oxygen is present, that is in the double bond, and towards this side also oxygen is present, and towards this side carbon is present. So this is a carbon atom which do not have any protons which is present to the adjacent carbon atom. So that is why, so we are going to observe so three different signals, even though two methyl groups are present. So this methyl group, so this is very far from this methylene group, and it has not founded any of the adjacent carbon or protons which are attached to it. So that is why we observe a different sort of interpretation in case of ethyl acetate. Okay, so this is how NMR spectroscopy is used to do the characterization of organic compounds. I hope you have understood it in a better way, and I wish you all the best for your examinations. Thank you.